Good afternoon. I just want to welcome you to the last in our seminar series of this year on advanced transportation technology. I just want to quickly remind you that after this seminar is over, there'll be a half-hour break and we're going to have some refreshments. And at 4:30, there's a Q&A to talk about women in academic careers. So any of you ladies, by the way, everybody's welcome, who wants to stay behind and just talk to someone who's been doing it for a while, discuss and answer your questions, you're welcome to stay. So I'm going to first let Kylie quickly remind you about this being a webcast seminar, and then I'll take over and introduce our speaker.
Thanks again, Max. As always, this seminar is streamed on the web, so to our remote viewers, please be sure to use the chat box to put your name, affiliation, and number of viewers so we can report it to the US DOT. Everyone in the room, please save your questions until the end. If you do have a question, you need to use the microphone, so I will walk around with the microphone if there are questions. For those of you viewing in on YouTube, please put any questions that you have into the chat box, and we will get to them at the end. But also keep in mind that there is a 30-second lag, so when your questions come in, we'll get to them as soon as possible. So thank you very much.
And before I forget, those of you taking the seminar series for credit, if you want to check on how you're doing after the seminar is over, please see Kylie, and she will share with you if there's still any requirements that you have to meet for the seminar in order to get the 1 credit. Let me introduce our speaker. I'm honored today to have Pat, I'm having a senior moment. Pat DeLucia with us. Pat has been a professor of psychological sciences and coordinator of the Human Factors Psychology Program, and is also Associate Vice President for Research at Texas Tech University. She's a fellow of the American Psychological Association, a fellow of the Human Factors and Ergonomics Society, and of the Psychonomics Society. She was the 2015 recipient of the Human Factors and Ergonomics Society's Paul M. Fitts Education Award. And by the way, if you're wondering who Paul Fitts was, look it up in Wikipedia, important person. And also the 2014 award from the American Psychological Association Division 21's Franklin V. Taylor Award. She's presently serves as the editor-in-chief of the journal called Human Factors. But let me add a little tidbit about Professor DeLucia. She started off being a baseball player, believe it or not, and she wanted to be a professional baseball player and played Division I softball and semi-professional baseball. And she decided to take a course in perception so she could learn how to hit the ball better. That is the start of her career in perception, and she received her PhD at Columbia University, then subsequently became a postdoc at Wright-Patt Air Force Base, and then joined Texas Tech in 1991. Without further ado, Professor DeLucia.
Thank you, Max, and especially thank you for arranging this and inviting me here. I have had a great visit. I've really enjoyed myself. I know how much time and effort it takes to put these things together, so very much appreciate you, Max, and thanks everybody for coming today. Today I want to talk to you about my research on the perception of collision, which represents the majority of my research activities. And so let me just give you an overview of my talk. I'm going to first put the research in a real-world context, talk about the importance of collision perception. Then I want to define some basic concepts, particularly regarding visual information for the perception of depth and collision. Then I want to mainly talk about my research showing the effects of the size of approaching objects on judgments of collision, and the theoretical and practical implications of that, and then I'll open up the floor for questions. So the creation and avoidance of collisions is common in everyday life. For example, drivers must control their cars to avoid collisions with other cars. And batters control their swings to make collisions between the ball and the bat. So how are these actions achieved? Well, to avoid rear-end collisions, drivers must recognize that the car ahead of them is getting too close, and they must estimate how much time they have before a collision is going to occur. To hit a ball, batters must select a pitch that they think is within reach and estimate how much time it's going to take for the ball to reach the plate. These tasks rely on the perception of depth or distance and the perception of time to collision, the time remaining until a collision will occur. Misperceptions of depth and collision can result in crashes. And I'm going to talk a little bit later about left-hand turns and motorcycle crashes. So the basic question that I've been pursuing for the past couple of decades is, how do people perceive depth and collision? And there are multiple sources of information, visual information, to support the perception of depth and time to collision. One class of information is the pictorial depth cues, or patterns in the retinal image that are associated with objects, locations, in three-dimensional space. Pictorial depth cues can be considered heuristics, in other words, rules of thumb, because they don't guarantee the correct solution, and depth cues do not typically define a single event. As you can see in this figure, the same retinal image or a given depth cue can result in an infinite number from an infinite number of three-dimensional environments. As an example, one of the depth cues is relative size. Closer objects in 3D space produce larger retinal images compared with farther objects that have the same three-dimensional size. Another source of information is an optical invariant. This refers to a higher order property of the light reaching the eye and is actually more reliable than pictorial depth cues. Invariants provide correct information and a one-to-one mapping with the property of the environment. So for example, you see this picture down here. An object occludes or hides the same number of texture elements on the ground plane, whether it is near or far, even though the size of that object on your eye is smaller when it's farther away. So the number of occluded texture elements on the ground plane, it remains constant or invariant with distance, and basically indicates that the object is the same 3D size at both near and far locations. When an object approaches the eye, it results in optical expansion. And within that expansion pattern, there is an optical invariant that provides correct information about time to collision. This graph here shows the optical expansion pattern. On the x-axis is distance. So going to the left, the object is approaching and getting closer and closer. And then on the y-axis is the rate of change in the object's visual image size, the optical size. As it gets closer, the rate at which the image grows gets faster and faster. And I'm going to show you an image, a video of this. You're going to see a square approaching you, and what you'll notice is it's getting bigger as it gets closer, but the rate at which it grows is faster as it gets closer. So the rate increases as it gets closer. And in that expansion pattern is the optical invariant called tau, which indicates the object's time to collision. We abbreviate time to collision as TTC, and again it refers to the time remaining until an object will contact an observer's eye, or more generally, the time remaining until one object is going to get to a certain location in space. In three-dimensional space, we simply compute time to collision by dividing distance by velocity. But the invariant tau is available in the retinal image, in the optical expansion pattern. And it will tell you when the object's going to hit you under certain conditions. The nice thing about tau is it does not require the observer to estimate distance or velocity. It's simply obtained by sampling the object's optical size at 2 different points in time. Specifically, as shown here, tau is the ratio of an object's current optical size by its rate of expansion, its expansion rate. Tau has received a lot of attention in the perception literature because it does not require the observer to use depth cues. It doesn't require cognitive processes. And tau is independent of an object's 3-dimensional size, its distance, and its velocity. Tau also provides relative depth information because as an observer moves through a cluttered environment, nearer objects are going to have smaller values of tau than farther objects. And so for all these reasons, tau has been the dominant explanation of how people make judgments about time to collision when an object is going to reach them. So in short, there are different kinds of information for the perception of depth and time to collision. The question is, which information will people use when multiple sources of information are available? And it makes sense. It's reasonable to think that people are going to use the most reliable information, tau, rather than heuristics such as depth cues. But my research has shown unexpectedly that depth cues such as relative size can affect time to collision judgments, even when the more reliable tau information is present. So we'll go back to the first study where I used computer simulations to depict a large object and a small object that approached the virtual eye at the same speeds while suspended above a ground plane. At some point during the approach, the objects disappeared so that the observers would have to predict the object's motion. As you can see in this bird's eye view, the smaller object was closer to the eye, and it would have passed the eye first. Now, the speeds of the objects were the same as each other and constant throughout the approach. The invariant tau, though, specified that the small object would reach the eye first. But the key manipulation was that the small object was so much smaller than the large object that it projected the smaller image on the eye throughout the approach. And this created a cue conflict situation. There was the depth cue of relative size, which indicated that the small object would reach the eye first. And tau, though, indicated, wait, did I say that backwards? It tricks even me. The small object said that the relative depth cue of relative size said the small object was farther away. But tau said that it would hit the eye first. So there was this cue conflict situation. And in the task, observers reported which object would reach them first had the objects continued approaching after they disappeared. So what we wanted to know was whether the small object would appear to arrive first, consistent with the invariant tau, or whether the large object would appear to arrive first, consistent with the heuristic, the depth cue of relative size. So I'm going to show you an example of a scene. And I want you to report to yourself which object you think would hit you first if the objects continue to approach after they disappeared. The object on the left or the object on the right? If you're like most people in the study, you perceive that the object on the right, the larger object, would have hit you first. And unexpectedly, in the first study, all 20 of the 20 participants in the study reported that same thing, that the large object would hit them first, consistent with the depth cue of relative size rather than with the more reliable invariant tau. And this effect of size on time to collision judgments has become known in the literature as the size arrival effect. And as I will discuss later in more detail, effects of size like this have implications for traffic safety because smaller vehicles may be perceived as farther away than they really are. When I first reported this result in the early 1990s, there were many criticisms of the study. People complained that the displays were too short. It was only a third of a second, the display. And that the resolution was too low. Back then it was like 640 by 480. Also, the objects didn't have any texture on them. And, importantly, participants simply made passive judgments. They didn't interact with the displays. They weren't active. But in numerous subsequent studies, the size arrival effect was shown to be robust. It occurred with longer display duration, higher resolution photographic animations of real approaching objects, and textured objects as well. And the effect of size occurred even with an active collision avoidance task, which I want to talk about next. In this particular study, we simulated self-motion toward a square object. The self and the square were both floating above the ground plane. And the square varied in size, but it was always located at the same starting distance, and self-motion toward it was always at a constant speed. The participants in the study were told to use a joystick to jump over the object, but first they had to get as close as possible to it. But they also had to avoid colliding with the object. And so what we wanted to find out was whether people would jump sooner to avoid collisions with the large object compared with the smaller objects, even though their heights were all lined up. And this is what we found. On the vertical axis, you see the observer's altitude as controlled by the joystick, and the horizontal axis shows time. The vertical line under the curve is the object, and so you can see we've got the small, the medium size, and the large objects. Notice that the top of the objects are all at the same altitude. And what you see here is that participants started their jump sooner to avoid collision with the large object compared with the smaller objects, even when the objects were approached from the same distances with the same speeds and the objects had the same heights. Interestingly, the same pattern of results occurred even when we enlarged just the width of the object or just the height of the object. And since this, the size arrival effect has been replicated with various displays, multiple kinds of tasks, and even in multiple labs across the country, including those labs where those initial criticisms first came. There are factors that reduce the size arrival effect. So, for example, it is reduced when you provide familiar size information. Here we see a marble and a beach ball. And it's reduced when you provide greater than normal binocular disparity information. It's also reduced when you provide display aids that show where the objects would have intercepted the ground plane. And the size arrival effect depends on the ratio of the object's projected sizes. The effect also depends on the object's rate of optical expansion. In other words, how fast the objects grow in the observer's visual field. So let's look at that. In the original study, there were two primary scenes, which I called the slow expansion scene and the fast expansion scene. Essentially, these were really two halves of a single scene. The slow expansion scene started farther away. The two objects approached, and then they disappeared. Well, the fast expansion scene started where that slow expansion scene left off. They started closer and then moved even closer. And so the fast expansion scene had greater rates of optical expansion. As you can see in this looming pattern, the two scenes were located at different points along the looming curve. And what I want to show you next is the fast expansion scene. Again, your task is to judge which of these objects would reach you first if they continued to approach after they disappeared. I imagine that most of you perceive the object on the left as sitting first. Now, this is the same exact scene, only it started closer. What do we find? Well, earlier when I mentioned the slow expansion scene, I mentioned that all 20 people picked the large object as hitting first. That's this big red line. With the fast expansion scene, nobody did. Everybody correctly reported that the small object would hit them first, consistent with the invariant tau. So as a prelude to the conceptual framework I want to discuss later, I want to note that this result indicates that the distance and the quality of motion information that you have is important in time-to-contact judgments. And this effect of distance has implications for transportation safety because drivers might rely on different types of visual information when they're making judgments about a far object compared to when they're making a judgment about a near object. And so they might need different assistive technologies for the two classes of distances. Effects of size are not limited to relative judgments in which people report which of two objects would reach them first. The effect of size also affects absolute judgments in which people press a button at the very exact time that they think a single object would hit them. And size also affects judgments about whether two objects would collide with each other, which we would call collision detection. So let me show you that. In the next video, you're going to see two cubes approaching each other. And your task is to judge whether the two cubes would collide with each other or miss each other. These cubes are unequal in size. You've got a large one and a small one. And in this scene, most people will report that the cubes would miss each other. They would not collide, even when, in fact, they would have collided. And you can see that in the next video. Here you've got ground intercept information. Is that right? Nope. Let me go back. Here we go. Here you've got the ground intercept information. So you can see, if you look at the arrows, that those two cubes would have collided with each other. On the other hand, if the cubes are equal in size, as shown here, most people report that the cubes would hit each other even when they would have in fact missed each other. And the next video shows the cubes with the arrows on the ground plane. You can see that the one on the right would actually have gone behind the one on the left. So the ground intercept makes it easier to make correct judgments. The implication of these results for traffic safety is that the size of moving objects can affect judgments about whether a collision would occur or collision detection. And collision detection is actually the first step in the perception of collision. You have to know if a collision is going to occur before you just have to judge when it's going to happen. And in this earlier study with the cubes, judgments of whether the objects would hit were actually less accurate for older observers compared to younger observers by about 20%. And so collision detection might be useful to consider when we evaluate differential crash rates in younger and older drivers. It's not necessarily just judging when the crash is going to happen. It might be the ability to detect whether a collision is going to happen. Relative size is not the only depth cue that affects judgments about collision. so can the depth cues of height and field, motion, parallax, and occlusion. So as you can see in this figure, what I mean by that is closer objects are located lower and move faster in the picture plane compared to farther objects. Closer objects also occlude or hide farther objects, and those are also depth cues, and they also affect judgments about collision. But it's not just depth cues that affect judgments about collision. There are other factors, including cognitive processes and affective content. Prior to our research, people typically studied relative time-to-contact judgments using two objects. In other words, people reported which of two objects would reach them first. In our study, we showed people 2, 4, 6, or 8 approaching objects, and people had to report which one of those objects would hit them first. So we varied set size across trials, and in this line of research, we measured response time. What we found is that mean response time was greater with 8 objects compared with 2 objects, which is consistent with the idea of limited capacity processing. And since this study, there have been other studies that show that limits in cognitive processes can affect judgments of time to collision. The implication for traffic safety is, unsurprisingly, that drivers may respond to risks more slowly when there's multiple vehicles on the road compared to when there's just, 1 or 2. The more vehicles, the slower they might respond. In addition, my colleagues and I demonstrated that even affective content can influence judgments of time to collision. In this study, we simulated an approaching picture, and the content of the picture was manipulated by using images from the International Affective Picture System. These are pictures that have been rated for valence and arousal, and that is basically how we selected the pictures for the study. So as an example, a threatening picture showed an attacker with a knife or a biting snake, and a neutral picture showed a lamp or an ice cream cone. We also included scrambled versions of the pictures to control for low-level factors. So in other words, on the right here, it's the same picture, but same contrast, same color, same luminance, but it's jumbled up so that you can't recognize what the picture is. In this study, we had the pictures approach, and people had to press a button when they thought the object would reach them. So let's look at an example of this. How about Nicole? Can you be my participant? And can you clap at the exact time when you think the object would reach you? Very good. So that was the threatening picture. Okay, let's go again, Nicole. There's the neutral picture. All right. So what did we find? This graph shows the difference between the object's actual time to collision and the observer's estimate of time to collision. The lower the value indicates the earlier the judgment, and results indicate that participants responded sooner for the threatening picture compared with the neutral picture. And that only occurred for the original pictures, not the scrambled version. So you had to recognize what the picture was. We would not expect this result if people were simply using the optical invariant tau, which is independent of the pictorial content on the squares. So what we're showing then is that the emotional or affective content on the approaching objects can affect perceived collision. Based on this, we wondered, well, if threatening scenes can affect time to contact judgments, What about threatening facial expressions? Would they have similar effects? And so in this case, we used the faces that were used in a prior study by Oman and colleagues in the social psychology literature. What they showed is that if you ask a person to search a matrix of faces for a target face that's different from all the others, the participant will find the target sooner if that target face is a threatening face compared to just a neutral face. So that's why we use these faces, the threatening, neutral, and happy faces from that study. And as in the other study, one object approached, and people had to press a button when they think the object would hit them. So you can clap or you can blink if you want to indicate when the object would reach you. Here is the neutral face. And here is the threatening face. And then here's the friendly face. Well, we were pretty sure we were going to find the same results as the threatening pictures, but actually we did not find an effect of the emotional expressions. We wondered maybe this was because these were just line drawings of faces, right? They were abstract faces. So the next experiment in the series was to look at digitized photos of real faces. And these were all standardized from the NIM-STEM picture set. They were standardized for motion. So this is the neutral face. This is the threatening face. Very angry face. And then this is the friendly face. And unexpectedly, we still did not get an effect of the expression on the face on judgments of time to collision. So the bottom line is that threatening scenes, but not threatening faces, affect judgments about time to collision. And we think that's because with a threatening scene, you know what the threat is and you know what's going to happen. The attacker with the knife is going to stab you, the snake is going to bite you, but with a threatening face, somebody who's angry, you don't know what they're going to do. They could yell at you, they can turn their back on you, so the threat really isn't as clear. That's our theory as to why we got those differences. Well, how might we apply that? You know, we thought that maybe if we put threatening images on the back of the windshield at certain critical times, people might respond sooner to potential rear-end collisions. And we actually did some pilot studies on this, and we did not find an effect. So we haven't pursued this for a while, but that was where our application was going to be. The relevance of this research is that it shows that visual information is not the only factor that influences judgments about collision. Limits in cognitive processes and affective content also can influence those judgments. And the implication for traffic safety is that factors that contribute to a crash are not limited to visual factors, such as a driving not seeing a vehicle or a pedestrian. The driver may see that vehicle or pedestrian, but may not perceive their distance or their time to collision accurately. Now let's return to the effects of size on collision perception. You might wonder why people would use heuristics like depth cues when invariants such as tau are available. And we thought about that question. We think there's some good reasons for that. The first reason is that tau provides correct information, but only when certain conditions are met. One of those conditions is that the object must move at a constant velocity. Second, the visual system is limited in spatial and temporal resolution. So for example, in order for someone to use tau, the increase in the approaching object's image on the eye must be above detection threshold. So people may not extract tau effectively if expansion is below threshold, and when might that happen? If it's a small, far, slow-moving object. And then third, cognitive processes are limited. People may not be able to extract tau effectively when the cognitive demands are high, and that might occur when people have to look at multiple objects, as I mentioned in that earlier study. So in other words, although tau can provide correct information, it's not always effective, and it's going to be constrained by limits in sensory and cognitive processes. And to me, it seems highly adaptive for the visual system to rely on other sources of information, including heuristics. Imagine if we could only use tau. We'd be stuck when it was below threshold, for example. The size arrival effect has theoretical implications. First, judgments about time to collision are based on multiple sources of information, including heuristics. And that means that the size arrival effect brings into doubt a theoretical premise in the literature that a single optical invariant is the basis for visually guided actions. In our context here, it raises doubt about the idea that tau all alone is the basis for time to collision judgments. And that means that it becomes important to determine the conditions under which different kinds of information contribute to time to collision judgments and how those different kinds of information get integrated. And toward that aim, I developed a conceptual framework for studying time to collision perception that I want to briefly describe. The motivation for the framework came from studies of the size arrival effect, neuropsychology studies, neuroimaging studies, and other behavioral studies, but especially on Goodale and Milner's proposal that there are two functionally distinct visual systems. According to Goodale and Milner, both systems originate in the primary visual cortex, but the dorsal system travels upward toward the posterior parietal cortex, and the ventral system travels down toward the inferior temporal cortex. Goodale and Milner proposed that the dorsal stream serves visually guided actions, as in catching a ball, and the ventral stream serves conscious perceptual judgments, as in identifying a shape. My main hypothesis is that there are three factors that are critical in the determination of whether time-to-contact judgments are influenced mostly by invariants or mostly by heuristics and cognitive factors. And those three critical factors are viewing distance, the nature of the task, and the motion that is present. The first dimension is the distance between the observer and the location to which the observer is attending. And let's just talk about the extremes. In the spaces immediately surrounding the observer, performance would be predicted by invariants such as tau. In extremely far spaces that result in low quality optical motion information, we would expect performance to be dominated by heuristics, such as relative optical size. The second dimension is the nature of the task. At one extreme, we have fast visually guided actions and expect performance to be guided by invariants. And at the other extreme, we have deliberate perceptual judgments, where we expect performance to be dominated by heuristics and cognitive factors. And then finally, the third dimension is motion, where at one extreme we have fast motion of the observer and objects in the environment with robust optical motion, optical expansion information. In that case, we expect domination by invariants. And at the other extreme is slow motion of the observer and objects, with maybe the optical information is below or just above threshold. And in that case, we would expect performance to be mainly influenced by heuristics and cognitive factors. When you put it all together, it leads to this pictorial representation of the framework, where you have at one extreme perceptual judgments of very far, slow-moving objects that are going to be dominated by heuristics such as the depth cues, and cognitive processes. At the other extreme, we have fast actions directed at very near fast-moving objects that we expect to be predominated by invariants such as tau. And to me, at least, it makes very intuitive sense because when objects are far away, there's time to consult memory and other cognitive processes before a response is needed. When the objects are close and moving rapidly, you might have to respond very quickly, and there's no time to consult memory. So it seems most efficient to use invariants in that case. Another important implication of this framework is that the information that affects collision judgments changes during an approach event. And this has not been considered in prior studies of time to collision, as is implicated by the typical methodology that has been used. In most studies, the participants in the study will view the entire approach event of an object approaching. And then at the end, they will make a single time to collision judgment. And it's then assumed that the results from that single judgment reflect the information that was used by the observer throughout the entire event. But that may not be the case. What we need is a methodology where judgments can be measured continuously throughout the approach event. And toward that aim, I developed scenes in which two spheres approach the observer. Participants used a joystick to report which object would reach them first, and they made those judgments continuously throughout the approach event. In this next video, I'm going to just demonstrate the task. You can see that there's a cursor on the screen, and it goes back and forth to indicate which object the participant thinks would hit them first. So it's the right one, then the left one, right, left. And that cursor's position as a function of time is recorded continuously throughout the approach event. The next video shows one of the real scenes in the study. And you can see here that at first, the participant selects the right object, thinking it's going to hit first. But then at the last minute, they switch to the other object, thinking it's going to hit first. And what I did here is I designed the scene so that the relative optical sizes and the relative values of tau of the two objects reversed at specific points in time. And what I wanted to find out was whether response reversals, judgments that reversed, occurred at the same time that those optical parameters reversed. In the scene of most interest, the values of tau of the two objects reversed during the scene, indicated by the arrows in this graph. So on the horizontal axis here, you have time. On the vertical axis, you have the value of tau. And here are the circles. This is the object that would actually hit first. And you can see that at the beginning of the scene, it had the smallest value of tau until you get to about 3,000 seconds. Then it flips. And now it has a longer value of tau compared to the other object. And again, at 7,000, it flips again. Now it has the first value of tau. So the relative values of tau flip, reverse, twice during the approach scene. So if people were using tau, we should be able to see them reverse their response twice during the scene. On the other hand, if people use optical size or expansion rate, they would not show any response reversals because the optical parameters did not reverse during the scene. Essentially, the observer would incorrectly pick the object with the largest optical size and the largest optical expansion rate throughout the approach event because they never reversed. This video shows the actual scene where tau flips twice during the approach event. And the way we achieved this is we modified the velocity. The velocity wasn't constant throughout the approach event. So what did we find for this particular scene? Of the 30 observers in the study, 17 of them selected the sphere with the larger optical size and faster expansion rate and never reversed their responses. They incorrectly picked the object that would have hit second. They picked it as hitting first. They clearly did not use tau. But 13 of the people in the study appeared to use tau. They selected the first arriving sphere, which had the shorter value of tau, and then they reversed their answer in the middle of the scene. So that pattern of response is consistent with the use of tau. These results clearly show that there are individual differences in the information that people use. Now that's just one scene. There were a variety of scenes. Overall, just a general pattern, the results indicate that when the approaching object was far away, people's responses were consistent with the use of heuristics, such as the relative optical sizes or the relative optical expansion rates. But the responses were not consistent with the use of tau, and that's what I predicted from the conceptual framework. When objects are far, people aren't going to use invariance. When the approaching objects were near, most of the observers' responses were consistent with their use of optical expansion rate, not optical size, optical expansion rate, but not with tau. Optical expansion rate is also a heuristic. Now that finding is not consistent with my framework, which predicted that people would use tau when the objects got closer and closer. Now, of course, it's possible that maybe the objects didn't get close enough, right? Because I was constrained by what I could simulate on the two-dimensional screen. And so further investigation is needed for that. Those were the theoretical implications. Now, the work also has implications for driving, because drivers might use different information and rely on different processes when viewing near and far spaces of traffic scenes. So, for example, they might rely more on optical expansion and tau when cars in front of them are near. They might rely more on cognitive processes when cars in front of them are far. And that also implies that they might need different kinds of warning systems or other aids to help them make judgments about events in near and far spaces. We looked at that a little bit with a study where people responded to the deceleration of a lead car using car following scenarios. What we wanted to find out was whether drivers' responses to a lead car's deceleration are affected by optical expansion information and by discrete warning signals that are completely independent of optical flow. We also wanted to know whether any such effects depended on the distance and the deceleration rate of the lead car. In other words, on the effectiveness of the optical expansion information. We had 12 undergraduates who were licensed drivers viewing a custom driving simulation of car following scenarios. And they were simply instructed to press a button as soon as they saw the lead car decelerate. We varied the time that the lead car decelerated so they couldn't predict the onset of deceleration. We varied the temporal headway to the lead car and the lead car's deceleration rate. We also varied the presence and the onset time of the lead car's brake lights and the presence of auditory tones that occurred when the lead car started to decelerate. So this is an example of a scene. The brake lights did not flicker in the real study, but it does here. So you see the car, and the task is to press a button as soon as it starts to decelerate. This graph just shows some of the main effects in the study. It shows the mean response time to the lead car's deceleration for some of the variables of most interest. And what I want to point out here is that mean response time was relatively shorter for the near headways compared to the far headway, and it was faster for the fast deceleration rate compared to the slow deceleration rate. The implication of that is the response to deceleration was affected by the effectiveness of the optical flow information, because expansion rate is faster for near headways and fast deceleration rates. In addition, the effects of the auditory warnings and the brake lights, there were effects of those, but only when deceleration rate was slow and headway was far. The implication of that is that people relied on these discrete warnings when optical flow was relatively less effective, when the expansion rate was slower. And that leads to a counterintuitive practical implication that maybe drivers need warnings more when the decelerating lead car is farther away. They might need the warnings less when the lead car is near, because when it's near, they can actually use the optical expansion information effectively. Now let's consider the practical implications that the size arrival effect has for transportation safety. To drive safely in traffic, drivers must effectively perceive possible collision events that, for example, occur when a person is turning left amidst oncoming traffic. If small vehicles appear farther away than actual, the driver may turn too late and may collide. And in fact, Card and Hancock, in a study that was actually done here, showed such an effect of size on left turn judgments using driving simulations. They simulated a left-hand turn scenario, and they had the oncoming car vary in size. They were motorcycles, cars, or delivery vans that approached the intersection. And participants were asked to press a button when they thought that oncoming car would reach their location. They responded later to small vehicles compared with larger vehicles, completely consistent with the size arrival effect. Similarly, the size arrival effect may have important consequences for motorcycle crashes. Notwithstanding, you've got the single vehicle crashes. When you've got crashes between two vehicles, most of the time when it involves a motorcycle, it's because the other driver violated the right-of-way of the motorcycle. Now, for a number of these crashes, the drivers do not see the motorcycles, but even if they do see them, a motorcycle's speed and distance may be misperceived because of their small size. And it was Horswell and his research team that proposed that the size arrival effect may contribute to these crashes. And they supported that idea with empirical data using a study that was similar to Card and Hancock's with videos of approaching vehicles. These studies show that the vehicle size should be considered when analyzing traffic crashes and designing countermeasures. In our most recent study, published in Accident Analysis and Prevention, we measured overtaking judgments in 24 undergraduates who were licensed drivers. And we used a StySim driving simulator that presented a car-following scenario. We wanted to know whether the size of the oncoming vehicle in the opposing lane would affect their overtaking decisions. When they were signaled by a tone, the participants had to report whether it was safe to overtake, to pass the lead car. The oncoming vehicle varied. It was either a motorcycle, a town car, or a large truck. And we also varied the temporal gap size so that half of the gaps were safe and half of them were unsafe. These graphs show the percentage of trials in which participants accepted gaps as safe and the percentage of trials in which they made false alarms. They accepted gaps that were not large enough to overtake safely. As you can see here, participants accepted more gaps and had more false alarms when the oncoming vehicle was a motorcycle compared to a car or truck. So they thought it was safe more often to overtake when the oncoming vehicle is a motorcycle. Now there was a weakness. There is a weakness of this first experiment, and that is the size of the vehicle is confounded with the type of the vehicle, right? Trucks are larger, but they're also trucks. And one can argue that maybe you don't think you're going to get as hurt by a motorcycle as you are by a truck. So we did a study to tease apart these two factors. We reduced the size of the original truck until it was the same size as the motorcycle. And we also increased the size of the original motorcycle until it was the same size as the original truck. And so that allowed us to compare results among a small motorcycle, small truck, large motorcycle, and large truck. And as you can see in this graph, the effect of size on accepted gaps and false alarms remained. There were more accepted gaps and false alarms for small vehicles compared to large vehicles, regardless of the type of vehicle that it was. So it was size per se and not vehicle type that accounted for our results. These studies show again that vehicle size should be considered when analyzing traffic crashes and designing countermeasures. To summarize, the size arrival effect has important theoretical and practical implications. It shows that collision perception is based on multiple sources of information, and that's important to consider when developing models and theories of the perception of collision. And the size arrival effect also has practical implications, for example, possibly resulting in small vehicles appearing farther away than actual and posing an increased risk for collision. Thank you for your time. I'm happy to take some questions. And again, thank you for hosting me. I've really enjoyed my visit.
Anyone with questions? And I will get the microphone out to you.
So I'm curious about train crashes, because it seems like drivers do risky things and underestimate the speed of a train, and you would think based off of this it would be the opposite because it's so large.
Yeah, that's an outstanding question, and it's sort of a conundrum. One of the big differences between train crashes and these kinds of studies I'm talking about is that the train is coming from the side. And in most of my studies, I'm looking at approach. And the optical expansion pattern is very different. For lateral motion, it's really quite highly linear, whereas in the expansion pattern, as you saw from the looming curve, it's very nonlinear. But it's a really great question, and one I know that Leibowitz talked about, basically attributing it to a misperception of speed, that larger objects appear to be moving more slowly. And that was an American scientist a long time ago. There was a recent study by Petzold who asked the very question, and I'm still reading that paper to try and understand why we have this discrepancy. It's a really good question.
There's a lot of interest in analyses of perception of using sort of models to figure out how well cues are combined based on the reliability of those cues. So you can sort of estimate based on noise measurements or threshold measurements how reliable any given cue might be, and then determine whether people are optimally combining the information. I wonder if that kind of analysis would be relevant for collisions.
Yeah, I do think it is. And there's I forget the person's name that published that study. I think it was in the Journal of Vision. Right?
A number of them, yeah.
A great study that looked at the different cues based on the reliability of those cues. I do think that it would be useful to maybe apply here. One of the things we're looking at is, in that vein, is looking at the relative weights of different cues that go from hearing and vision. So, because there's auditory tau as well. And so what if you have auditory tau and visual tau together? Does that make you more accurate than if one or the other? So great question. The integration of cues, I think, is really critical.
Yeah.
Thank you.
Yeah, this is very interesting stuff, and it kind of brings to mind some stuff we did actually back when Peter Hancock was still around here, where we identified intersections where older drivers are overrepresented and compared them to ones where they weren't. And the dominant crash type where the overdrivers were overrepresented was a left turn crash, and it was a right angle crash for the other ones here. So what that brings to mind is any ideas about, from a road design standpoint, could we be providing additional visual cues than the way the visual environment is laid out that might improve time to collision estimates?
You know, that's a really great question, because one of the things we've been wondering about lately is whether we can train people to use better cues like the tau information. And I think, you know, one inclination is to use attention manipulation. So, you know, what if you train a person to look at the bottom part of that car? Because, you know, these scenes that I've been showing you here, they're symmetric about the horizon, right? So they expand symmetrically. Well, that doesn't happen on our roads, right? The car's on the ground, so they actually move downward in the visual field, which is more linear of a change than the expansion. And so I've been wondering whether you can teach people to look more at that component of the optical pattern, and maybe they'd be more accurate. I don't know. That's an empirical question. But I don't know in terms of visual cues in the environment, because I bet if they worked under one set of conditions, when the lighting changed and it went from daytime to nighttime, like, it may not carry over. But maybe with all the new technologies that we have, maybe using auditory kinds of cues might help to augment the judgments.
I think we're running out of time. One last question, and then we'll call it quits.
So actually, I'm wondering about the mechanism behind the size effect. So I'm wondering whether it is a perceptual process or actually sometimes it's a cognitive process. For example, in the overtaking experiments, is it possible that the judgment is actually affected by the judged severity of a collision? For example, it's presumably more severe if you collide with a truck, a bigger stuff, than to collide with a small stuff like a motorcycle. So does the participant just becomes more conservative? I mean, when it is a truck that's
right on target. And that actually one of our next experiments is going to be where we replicate that study, but the vehicles that are oncoming, they're going to be on the other side of a divider, so that a collision actually can occur, but you still have to judge their time to collision. So now we take the harm out of it. They can't actually crash with you because you're not passing, but you still have to make the judgment. So will we get that same effect or not? Because here we didn't tease apart that factor, which is still a relevant factor. Yeah.
Anyway, please join me in thanking Professor DeLucia for her presentation. And again, there will be refreshments right here afterwards. Anyone who wants to stick around. Thank you.